So today we're going to talk about ultra high temperature materials for aerospace applications in development. So when we say ultra high temperature materials, these materials are specifically for the combustion section of a turbojet or a turbofan engine. So this is the first Rolls-Royce Wayland. Now, what's special about this engine? This was the first ever engine to be developed by Rolls-Royce in Britain in 1942. And this engine was kind of a top dog, or you can say an engine which kind of paved way to all the future generations of jet engines or turbojet engines ever developed in the history of humankind. So now Rolls-Royce currently has a Trent 7000 engine, which is one of the most beautiful and technologically advanced turbofan engine. So let's talk about what a turbofan engine looks like. So in a turbofan engine, you've got one shaft on which you have got the main fan, which sucks the air into the engine, and then you've got the compression turbines, and then you've got the high pressure turbines, which kind of compresses it to a huge extent, and then a fuel is spread into that section to combust it using the hot air which has already been sucked into the engine. And from the exhaust side, the thrust releases, which creates a reaction in the opposite direction, according to Newton's third law of motion, and that propels the aircraft forward. So the combustion chamber is kind of a place where you require materials which will sustain high fatigue strength, which has high creep resistance, and which will live up to the expectations of high temperatures generated in that portion of the engine. And then you've got another variant of this engine called as turbojet engines, which has got huge compression ratios. And again, in the combustion section as well, the turbines also face the same dilemma or the same properties they require in the turbofan engine.
So here is a chart of a lot of the different materials that are used in different sections of engines. So we're going to focus on the materials used in the combustor because that's where the highest temperatures are reached. So you can see that GE, Siemens, and Westinghouse all use primarily nickel-based superalloys to make up their combustors. So these materials, the Hastelloy-X, the Mnemonic, the Haynes 188 and 230, are nickel-based superalloys that are most frequently used by companies to make engines and combustors for those engines. Nickel-based superalloys, as we talked about, are extremely creep resistant and function at extremely high temperatures, but they do have some downsides in that they're expensive and they are very, very heavy.
So nickel-based superalloys, they were mostly used in the combustion sections for like past 10 or 15 years. And so I'm going to tell you an interesting story about how one of the most famous nickel-based superalloy called as Mnemonic 88 came into being. So on the left side, you can see temperature. You can see a picture for the first stage turbine blades built using Mnemonic 88. So it was from this point where the Mnemonic 88 was used, or you can say developed from steam turbines into gas turbines. And on the right hand side, you can see the gamma prime phase developed for the mnemonic 80 at different temperatures. Now, the reason why to show this picture was that mnemonic 80A was kind of a material which was one of the first precipitation hardened materials ever to be developed for jet engine applications. And so this is Rolls-Royce. So what's specific or what's amazing thing about this? This engine was designed and developed within 5.5 months during 1940 in the year of 1942, and it was developed urgently for World War II applications. And it was used in two famous jets ever flew in the history of mankind. It was the MiJ-15 and the War Supermariner. Both were used by British Navy. After using mnemonic 88, it was kind of developed into many more engines by different companies called as Pratt & Whitney, General Electric, and this kind of paved way to more advancements and development into the nickel-based superalloys.
And these developments have been ongoing. But as you can see, the aerospace industry is all about developing better and more efficient technologies. So one material that's a very interesting development that's come around recently are CMCs, which are ceramic matrix composites. So this chart basically shows the specific strength at different temperatures. And you can see that CMCs vastly outperform nickel-based superalloys. So CMCs are ceramic matrix composites where you have ceramic fibers embedded in matrices of ceramic materials. So they're processed from between 1200 to 1400 Celsius. And this allows them to be able to retain their strength at temperatures up to and over 1800 Celsius. So given that current nickel-based superalloys max out around 1100 Celsius, this is a huge improvement. These are images of the microstructures of these CMC materials. You can see that they're oriented fibers embedded in matrices, and the phases that you see depend on what you put into them. So CMCs can be made out of a lot of different materials, such as carbons, silicon carbons, aluminum nitrides, silicon nitrides, that all have different, basically different function based on the composition. So this is another chart that shows how they retain their strength up to and above 1000 Celsius to 1400 Celsius. The processing pathway for these CMCs is pretty intensive, which is one of the downsides as opposed to using a nickel-based superalloy. So you start with a silicon carbon fiber, you can do CVD to coat it, and then the processing continues until you get infiltration into this matrix form. At this point, you can use the matrix and the composite to form different structures and apply it for your engine parts. This is another graph that basically shows how the processing changes the temperature that it can function at. And so different processing methods will increase the maximum temperature even further. So silicon carbide can go up to and around 1300 to 1500 Celsius versus these new oxide-based ceramic matrix composites can reach temperatures around 1800 Celsius depending on how they're processed.
So now this is one of the most recent application of CMCs developed by General Electric Aviation. So this is the brand new General Electric 9X engine, and this engine employs the usage of CMCs into the combustion section of the engine. So this is where they actually use the ceramic matrix composites. It is used in the combustor section, and this has helped General Electric reduce the mass or the total weight of the engine. And this is kind of a huge development for General Electric as they shifted from their gears from nickel-based superalloys to CMCs. And this has helped them quite a lot in increasing their business for this jet engine section. So the next subtype or the subset of CMCs is the oxide ceramic matrix composites. So what are these? These are just the normal matrix composites which has been artificially manufactured to develop an oxide layer on them to make them more suitable for usage in varied applications. So this materials are specifically used in the most of the critical aircraft engine components where the temperature or the temperature of the combustion section or the different parts is way too high, which cannot be sustained by the materials currently being used. And the beauty of this material is that they have very low creep and high temperature resistance. So they can go up to 1100 and 400 degrees centigrade, which is pretty high compared to the materials currently being used. But the one of the drawbacks of this material is that it is quite brittle. And since that's why it has been quite difficult to use them extensively in the jet engine application. And now the research is ongoing about how to use them and to improve their machinability, to convolute or to convert them into the shapes actually required and desired by the application for the application in the combustion section of the engine.
So another category of materials that are in development are refractory multi-principal element alloys. So these alloys are very high entropy, where they have a lot of principal components, and that gives them different interesting chemistries and characteristics that you wouldn't get with your standard nickel-based superalloys. One of these that's been used extensively since the 1960s is C103, which is an alloy with hafnium, titanium, but a significant portion of niobium. And this basically gives it incredibly strong properties at very, very high temperatures with a fraction of the weight that nickel-based superalloys would have. So these niobium alloys can reach temperatures that are maximum operating temperatures of around 1500 Celsius. And they are easy to weld without fracture, but they do have downsides where they are much more expensive than niobium superalloys. It's around $35 a kilogram to $100 a kilogram in comparison. And they are nowhere near as ductile, and they're much harder to machine. So the way that these materials are manufactured is through vacuum arc melting, where you basically put the raw materials into a vacuum chamber and use arc welding to melt them down because they have such incredibly high melting points. Most of the refractory multi-principal element alloys are primarily composed of refractory metals like niobium and vanadium. In some cases, you can see tantalum or molybdenum used, depending on the properties that you want. So on the next slide, we have a graph that basically shows the yield strength versus temperature for a lot of different RMPEAs. You can see that different ones will have higher yield strengths, or different ones will be functional up to higher temperatures. And so C103 is a good balance between retaining strength and being able to operate above 1400 Celsius. So these materials are being used in aerospace. C103 was actually used on the Apollo shuttle, and they're very, very good for their super high temperature resistance, and they retain their strength. Metal is one company that's commercially developing these products, and you can see that they're used in ingot form as powders and as foils for protective coverings.
So what does the future looks like for these materials? Well, the CMCs are currently being used by General Electric, and also they are being under development by Rolls-Royce and Pratt & Whitney. But the major problem of using CMCs was because of the high cost. They have very huge manufacturing cost and very high machining cost as well. So if so, the future for CMCs looks like that it is going to be used extensively, and more research is ongoing regarding their machinability and reducing the cost factor.
But there's also a lot of different materials being researched. So an entirely new category of materials that are being looked at for high temperature applications are titanium carbides. So recently as 2020, in fact, there was research done that was shown you could use titanium carbides to increase the temperature and the yield strength of molybdenum silicon. So here we have some ternary phase diagrams that show different compositions that they found, which give these really high temperature resistance properties. This image on the right is a 3D microstructure of one of these molybdenum silicon alloys that have been added titanium carbide. And you can see that they're very intricate microstructures with different regions and segregation. And then under further investigation, you can see that there's a lot of different regions where you have some mixing of certain phases versus segregation of others. So there's solid solutions of molybdenum with phase T2 and also titanium carbides mixed in. And the implications of what this means for the yield strength and creep resistance aren't known yet because this research is extremely new and ongoing. But researchers are pretty confident that these materials are going to be useful in aerospace very, very soon. So to kind of wrap up our presentation, we found this nice graph that shows how the evolution of temperature and materials has evolved and increased over the last 100 years. So you can see that right now we're at nickel-based superalloys, which max out around 1150 Celsius. But these new materials such as CMCs, oxide CMCs, and refractory alloys are going to dramatically increase the operating temperatures, which will in turn increase the efficiency that engines can work at. And there's still new materials in development, but it's a really, really interesting field, and there's a lot of stuff that's coming in the near future.